Hi everyone, I'm Natalie, and I hope you're ready to talk about a time long, long ago. This summer for the YSP project, I worked with Sanjoy and his lovely research team with former YSPs Serhat, Dana, and Nicole to review early Earth literature and do some modeling. This is Archean Seawater, a missing puzzle piece, Reconstructing Early Earth Seawater with Geochemical Evidence and EQ3. The planet Earth is 4.5 billion years old and with a lot of stories to tell. What did it look like in its early days before oxygen filled the atmosphere around 2.4 billion years ago? Well, it took some time for the Hadean magma ocean to settle down, but when it did, the Earth had liquid oceans, a hotter mantle relative to today's temperature, increased degassing and volcanism into the atmosphere, about a third less solar energy than today's sun, and abundant hydrothermal activity. Around 3.5 billion years ago, depending on who you ask, life emerged as single-celled organisms. Stromatolite fossils represent Earth's earliest evidence of life. These cyanobacteria colonies are still extant today. They are depicted in the bottom right corner of this Archean environmental reconstruction. Our understanding of Earth's early conditions, including the chemical evolution of the oceans, is in large part derived from the geological record. There are countless unanswered questions about what happened on Earth in the past that ultimately led us to the Earth we know and love today. Physical samples of these conditions either don't exist or require immense interpretation to find answers. The ocean's chemistry has changed significantly over its lifetime. During the Archean eon, from 4 to 2.5 billion years ago, the atmosphere and ocean had little to no oxygen, until the Great Oxygenation event that started around 2.4 billion years ago. The GOE saw fluxes in, for example, dissolved iron and silica, molecular hydrogen generation, and carbon and oxygen cycles. It wasn't until 2 billion years ago that eukaryotic life evolved, and 500 million years ago that it proliferated. We don't have a sample of what constituted Archean seawater, so we use mineral proxies and geochemical evidence to reconstruct the past. Our goal, after reviewing an array of Archean literature this summer, is to quantify potential chemical compositions of the Archean Ocean. Rather than assuming a single Archean seawater composition, we're trying to constrain the major components individually and then combine those constraints into chemically consistent Archean seawater models. Geochemical systems have many moving parts: mineral phases, saturation, reservoir fluxes, speciation, and chemical reactions, to name a few. EQ3 is a geochemical equilibrium software that models interactions between aqueous solutions, solids, and gases. It can predict which chemical species are thermodynamically stable in a particular environment. We are creating an input file with proposed seawater and rock and mineral concentrations such as iron, sulfate, oxygen, hydrogen, and silica. The program will equilibrate water-rock systems under varying conditions such as temperature, pH, and water-rock ratio, and generate an output file containing the calculated distribution of aqueous solution species and precipitated minerals. This here on the right is a screenshot from the EQ36 Linux terminal. This portion of the project is still in progress though. Because Archean seawater chemistry is poorly constrained, our understanding of early Earth's biogeochemical cycles, redox evolution, and environmental conditions that shaped early life remain uncertain. By constraining the major chemical components of the Archean Ocean, we can illuminate a piece of the puzzle. This has implications for the following: the environments that were conducive to the origin of life, metabolic pathways, and biological evolution and proliferation, early Earth systems and how the atmosphere, ocean, mantle, and crust interacted in the past, paleoclimate and its applications to modern climate change and greenhouse gases, and finally, perhaps we will be a step closer to understanding the ever-enigmatic banded iron formations. Thank you for listening. I have really enjoyed learning so much from this project, and I am so grateful to have met and worked with the team. And here are my references for this presentation.